solve a problem. A sphere of radius 6 cm carries a uniform volume charge density 450 nanocoulomb per meter cube. What is the total charge on the sphere? Well, you can do that very easily. Total charge on the sphere will be the volume of the sphere multiplied by the value of the volume charge density. This is rho. Rho multiplied by the volume will give you the total charge on the sphere. Find the electric field at r equal to 2 cm, that is inside the sphere, r equal to 5.9 cm, again it is inside the spherical object, r equal to 6.1 cm outside, r equal to 10 cm is again outside. Alright, let's get going. The radius of the sphere is 0.06 meter, 6 centimeter. Rho, the volume charge density, is 450 nanocoulomb per meter cube. Well, this is not written correctly. You must write it nanocoulomb per meter cube. That is the unit of rho. So that will be like this, nanocoulomb per meter cube. There's an M missing in between there. And what else do we know? We know rho, oh well, I just repeated it with the same mistake. The total charge Q is the volume of the sphere multiplied by rho. 4/3 pi r cube. R is the radius of the sphere. So 4/3 pi r cube is the volume multiplied by rho. And the volume is 0.06 meter. And that is 4.07 times 10 to the negative 10 coulomb is the total charge carried by the sphere. We now want to find the electric field at r equal to 2. R equal to 2 is inside the sphere. What is the expression for electric field inside the sphere? E sub r is rho over 3 epsilon naught times r. We know rho, we know epsilon naught, we know r equal to 2 centimeter, that is 0.02 meter. So use all those values there, we get the electric field is 339 Newton per coulomb. Well, what is the electric field at r equal to 5.9? The same relation. Our r now is 0.059. So replace that r by 0.059. Everything else remains the same. And that field is 1000 Newton per coulomb. You can see as we move away from the center towards the surface, the electric field increases inside the spherical conductor or the spherical charged object. And now I want to find the electric field at r equal to 6.1 centimeter. That's a point outside the sphere. And the expression for the field outside is 1 over 4 pi epsilon naught q over r squared. This can be replaced by kq over r squared. Alright, let's use this relation anyway. Alright, q, the amount of charge on the sphere, is 4.07 times 10 to the negative 10. 4 pi times epsilon naught times r squared. That is 983.5 Newton per coulomb is the electric field at r equal to 6.1 centimeter. How about the electric field at r equal to 10 centimeter? Well, the only difference is this distance where? This distance 0.061 we used earlier will now become 10 centimeter or 0.1 meter. there you are, and that value is 366 Newton per Coulomb. Well, problems, once you know the basic method, problem solving in these areas are fairly simple. We will now use Gauss's law to find the electric field at a distance r from an infinitely long charge. Well, this is a long object. An infinitely long charge will extend to both sides, and I want to find the electric field at a distance r from it. And we're going to use Gauss's law. What is the method? Well, the method is, every time you want to use Gauss's law to find the electric field at a point, you need to construct a Gaussian surface that contains the point. And the Gaussian surface must enclose some charge from the object that we are using. That means if I want to find the electric field at this point, I must use a Gaussian surface that will be a cylinder that will enclose part of this infinite charge. You see that? So I have to find the electric field at this point. I will take a Gaussian surface that will be a cylinder that will enclose a certain length of the infinite charge. Okay, that's the method. Let's go. Consider an infinitely long charged conductor which has a charge per unit length lambda coulombs per meter. The linear charge density. Now, this is the infinitely long charged conductor. We need to find the electric field at a point distance r from this charge. So what do? By symmetry, the field lines radiate uniformly outward if lambda is positive and inward if lambda is negative. So if this is a positively charged object, the field lines will radiate outward. Is that right? That means the field lines will be crossing this cylinder at right angles in that direction and also downward. All over the spherical surface, the field lines will be radiating outward. If the charge on this is negative, the field lines will be directed inwards. Now we take a Gaussian surface, which is a cylinder enclosing a length L of the charged object. Is that right? And the point where we want to find the electric field is on the surface of the Gaussian surface. It's very important to know that. Now, if R is the radius of this cylinder, you see, the cylinder we constructed has a radius R, means R is the distance of the point where you want to find the electric field. Then what is the surface area of this cylinder? Can you figure out the surface area of the cylinder? Let's take one more look at this. Suppose this is the infinitely long charge and I want to find the electric field at this point, the distance r from it. What do? I construct a Gaussian surface that will be a cylinder of radius r. Let me see if I can construct that cylinder. Alright, I'm struggling here. Well, here is the cylinder and the charge inside. Alright, what is the surface area of this cylinder? Alright, my charge has fell off. This is the Gaussian surface, right? What is the surface area of this? The surface area will be, if I straighten it out, this will be the surface area, which is given by this length multiplied by this width. But this width, when it is a cylinder, is a circle of radius r. Is that right? Now, that circle has the radius r, so that would be 2 pi r times the length, that is the area. So the area of the Gaussian surface is 2 pi r times the length. This is 2 pi r times the length is the area of the Gaussian surface. Why do we need the area? If E is the electric field at any point on the Gaussian surface, then what is the net flux crossing the Gaussian surface? The net flux crossing the Gaussian surface will be its area multiplied by E. What does E stand for? E stands for flux per unit area. So phi net equal to the area of the Gaussian surface multiplied by flux per unit area, that is the electric field. Well, we now know the net flux. Now, do we know the amount of charge inside the Gaussian surface? Well, inside the Gaussian surface we have a length L of the charged object, and the linear charge density is lambda. Therefore, what is the amount of charge carried by that length L? It will be L times lambda. The net charge inside the Gaussian surface of length L is Q inside. That is, the amount of charge inside the Gaussian surface is L lambda. Now, we know phi net, we know Q inside. We can now use Gauss's law. Phi net equal to 1 over epsilon naught times Q inside, or 4 pi k times Q inside, whichever equation you want to use. Well, phi net equal to 1 over epsilon naught times Q inside. Phi net is 2 pi r LE, and Q inside is L times lambda. And now, I can now cancel L on either side and solve for E. What is E equal to? E equal to lambda over 2 pi epsilon naught times 1 over r. Now, why I wrote like this? Because lambda over 2 pi epsilon naught is a constant. And that means field at any point varies inversely as the distance from the charge. As you move away from the charge, as the distance r increases, the field decreases. Well, this is the expression for the electric field at a point distance r from an infinitely long charged conductor. All right? Let's now